Good evening. Thank you all for coming tonight. It's always a pleasure to be here. I think I've been here 3 or 4 times. I can't remember. It's been a while, probably a year and a half since I was here last. And tonight I'll be speaking about the James Webb Space Telescope and what it's revealed about the universe. Generally, I'm just going to shorten James Webb Space Telescope. That's a mouthful. I'm going to shorten it down to JWST. Is that okay? Hopefully so. And I've found that many people don't really understand much about the telescope itself, and that's very important to know. Probably one thing you've heard many times is that it's a replacement for the Hubble Space Telescope, or the HST. Y'all heard that before? Well, it's not quite true. It's a very different telescope in many respects. So I'm going to start with a description of the HST and talk about it a little bit. Do you realize it's been orbiting now for 35 years? It's an old telescope, folks. No wonder we want to kind of upgrade it a little bit. It is an optical telescope, which means that it works primarily in the visible part of the spectrum. You know, at one end of the spectrum you have red, that's a longer wavelength. Other end is blue or violet, that's the shorter wavelength. But it does extend a little into the ultraviolet. Beyond that, at shorter wavelengths yet, we can't see, and then a little into the infrared, but not very far from what we can see. There are 2 reasons for putting telescopes into orbit. One reason is to get above the ocean of air that we're in. There's a lot of turbulence in the air, and it tends to really fuzz up the images. If you see stars twinkle, that's an indication of the atmosphere that's got a lot of turbulence. A lot of twinkle is really bad for astronomy. We want steady skies. So the HST was put above the Earth's atmosphere to avoid that aspect of the thing. On the other hand, there's another reason for putting things into space, and that's because certain parts of the spectrum are blocked. Once you get into the ultraviolet, the atmosphere of the Earth blocks anything, much of the ultraviolet, anything shorter wavelength than that, and that's a good thing. Why is that? Well, if you're exposed to UV light from the sun, what happens short term? Sunburn, long term, cancer, degradation of your skin, age spots, all those kind of things. What if you go beyond that into the gamma rays and X-rays and things like that? Not good at all. It will kill you pretty quickly. In fact, if you're above the Earth's atmosphere and you're exposed just to the UV light of the sun for 5 or 10 minutes, you'd probably get a lethal dose. It would not be a nice way to die either. So it's good we have the atmosphere there, good for living things, but bad for astronomy because there's a lot of stuff we want to access there. On the other end, as you get into the infrared part of the spectrum, a little bit of that gets through, but much of that is blocked too. And there's a lot of information found there we can only get by going into orbit. Once you get over to longer wavelengths into the radio, much of that actually does make it through. So we have the shorter things in ultraviolet and shorter, and we also have infrared, which we don't really get on the ground. Now, again, the Hubble Space Telescope, it's doing in the optical. Don't worry about those other wavelengths too much. It has a 2.4 meter aperture. When I say aperture, I'm referring to the size of the mirror or lens. And some telescopes, but most of them today have mirrors. 2.4 meters, that's about 8 feet or so. They built, there's a picture, this was taken by one of the service missions to it. Photographed in space, actually. And they built it so as big as it could be and still fit inside the cargo bay of the space shuttle. Because that's what they used to launch it. They would have needed a rocket otherwise to do it. Also, it has a single mirror, a single piece of glass for that large aperture telescope. By the way, 100 years ago, that would have been the largest telescope on Earth. But it's kind of puny by today's standards. We have a couple of 10-meter telescopes. Those are 33 feet across, but they're ground-based at that point. Another key difference is the point is that the HST is in low Earth orbit. It's a few hundred miles up. They put it there because that's where the shuttle could go. The shuttle cannot leave low Earth orbit. You may have seen, fictional programs of the shuttle going off, leaving the Earth, going to the moon. Can't happen. It didn't have the capability to do that. It was only going to low Earth orbit and back again. So if you're going to go up and service it, you need to keep it in low Earth orbit. By the way, the orbits of things in low Earth orbit, their orbits decay by a little bit of wind resistance. There's a little bit of air up there. And eventually, if nothing's done, the HST will fall back into the Earth's atmosphere and burn up. Most of it will. The mirror will come through intact, probably. There is some discussion of having a special mission at some time to go pull it down and bring it back and put it, at least the mirror, in a museum. We'll see about that. But it is 35 years old. When it does finally give up the ghost, it's probably just for the better, because it's going to have wear and tear on it and things are going to wear out. And they're not planning any more service missions to it like they had when the shuttle was running. Now, what about the JWST? Well, it's shaped very differently. And one of the first things right out of the gate is that it's an infrared telescope. It goes a little bit into the visible, into the red part of the spectrum, but there's no yellow, green, no blue. It's not even, doesn't have detectors or abilities to see that. It goes on into the near infrared and to the mid infrared. We've never really done that before. In the past, we've had several orbiting observatories that were infrared, but they didn't really have the full complement of instruments that this one has. This is a really specialized thing. Now, it brings up an important point. We can't see infrared. So when you look at many of the images that have been produced from the Webb Space Telescope, you are looking at false color images. They have several wave bands that they can take pictures, but then you have to color code them somehow. So when people ask me sometimes, these pictures from space, from different spacecraft, are they giving you real colors? Well, tell me which mission you're talking about. I have seen photographs that combine radio measurements, ultraviolet and gamma ray. Not a bit of visible there, and they made it color coded so you get this pretty picture, but none of it would the eye actually see. So I'm telling you again, except for that one red filter they have, one red band that they have, all the images you see, if they're color images from the JWST, they're false color. And that's okay. The colors actually do mean something. So besides being a pretty picture, you can see some science in it as well. It's a larger telescope. It's 6.5 meter aperture. That means it's nearly about 2.7 times larger with about 7 times the collecting area. So you can collect 7 times more light than you would otherwise. Now, to get that into space would be pretty tricky, that thing being that big. So instead of having a single mirror like the HST had, it has 18 hexagonal mirrors. You can see them there on this is, by the way, is an artist's conception. We don't have a picture of the JWST in space yet, or probably never will, because it's got a different orbit I'll describe here in just a moment. But those hexagonal mirrors were all folded up. And the struts on it and the sunshade down there, all those things were all folded up very nicely. And they had to plan this very carefully. Little motors that would open and click into position. And it took days to open this thing once they got it to where they wanted it in space. And you had, I think, like 360 different steps. Open. And if any one of them failed, you've just flushed a few $1 billion down the toilet at that point. So it actually opened perfectly when they launched it several years ago. Now, its orbit is interesting. It's at an L2 point, a Lagrangian 2 point. It's not in low Earth orbit. It's about 1 million miles away. Lagrangian points these are 5 locations with one smaller body orbiting a larger body where things can be parked and will stay there. You've got the Earth, the sun sitting here, and you've got the Earth orbiting around the sun like this. And if you just consider those two bodies, it's a simple problem. You can do that with basic physics you learn in high school. But the moment you throw a third body in there, it becomes what's called an in-body problem, becomes very complicated. And if it's a small object, the two other objects tend to move it around a lot. It'll be perturbed, we say, and it moves like this very slowly, but it gets moved around. But there are 5 places where it will stay put. You've got the sun here and the Earth here. I think the L1 point is between the Earth and the sun, but closer to the Earth. The L2 is on the other side over here. And you've also got the other 3, I never can keep the number straight. 1 is on the other side of the sun, and the other 2 are at 60-degree angles from where the Earth is. So you've got 1, 2, 3, 4, 5 points. If you park something there, it will tend to stay there. It's very stable. They picked to do this, they selected to put this at the L2 point, which means it's about 1 million miles beyond the Earth away from the sun. Low Earth orbit is a few hundred miles up. This is almost about 1 million miles up. So obviously, it's not placed there for a service mission. You're not going to go there. We put it there, and when it dies, we're just going to leave it there. So, 100,000 years from now, somebody might, the civilization's gone and somebody comes along and discovers this thing. Who put this here? What is this, No records of it perhaps, but it's going to be there for quite a while. Now, there's also a sunshade I just mentioned earlier. It's that big trampoline-like thing on the bottom side of it. It's got multiple layers, and that faces the sun. The sun would be below in this image, and so this thing is perpetually in shade. So why is that? Why the sunshade? Well, I want everybody to do this. Take your hand and place it like an inch or less from your face. Don't touch your face. And just do that. And what do you feel on your face? You feel heat, don't you? That's infrared radiation you're picking up. Because your bodies, if you had a totally dark room and you're wearing special infrared goggles, people would show up with these big glowing things sitting there. We don't see that. Some creatures can see those. Pit vipers, rattlesnakes, copperheads, they have those pit organs that they have in that triangular shaped head, and they're detecting infrared. In a totally dark room, a pit viper could see you in the dark. Nice thought, isn't it? Well, keep in mind that that snake is going to realize that you're really big, too big to eat. And they tend to view you as a threat, so they're going to leave you alone. Contrary to popular misconception, snakes generally don't go chasing after you. They would rather be left alone for the most part. Particularly copperheads, they're pretty docile. They really are. Not that I have a lot of experience with it, but I've seen them a number of times, and they just don't care if you're there. They really don't. But enough of that. We also have special missiles that we launch to take out airplanes, or heat-seeking missiles. They have infrared detectors, and they see the exhaust coming out of the back end of the plane, and it zeroes in on that. All you have to do is fire a relatively modest rocket with an explosive up the back end of an exhaust port on a plane, and the plane's not going to fly much very well without that. That's the reason why the A-10, the A-10 looks like the warthog. It's got those big fins in the back, the vertical stabilizers, 2 of them. It's there to kind of partially block that infrared signature on those. Awesome plane that one is. So warm things emit infrared radiation, including the telescope and the detectors on it, the different instruments, because they have temperature. I've only done infrared observations a couple of times over the years, and it's very frustrating. I do photometry in the visible part of the spectrum. I ventured into the infrared on 2 different programs that I worked on, and I did not like it because I can sit there with my photometer and I can measure brightness of a star, and I get like 50,000 counts with it. Now we're also measuring a little bit of the sky, so I move the telescope a little off to the side, so we just look at sky, and I get a few hundred counts, and I subtract that off, and I still have 50,000 counts. That's great. The first time I did infrared observations, I got like 300,000 counts on this. That's fantastic. I move it off to a bare part of the sky, and I get like 290,000 counts, and I subtract it off, and I'm left with just 10,000 counts. It's really rough because the sky itself is glowing, the telescope is glowing, everything's... Imagine a telescope in a dark location with a bunch of lights all over the telescope. That's basically what you're dealing with here. The way to get around this is to cool it. And one way to do that is with liquid helium. You have a dewar of liquid helium as it expands like refrigerant does and your Freon does in your AC systems and refrigerators. It cools things down. So we've had several orbiting infrared telescopes in low Earth orbit, and they were good in their day. The first one was launched 40 years ago, I think. But the problem is eventually the helium runs out. And when that happens, it warms up, and then suddenly it's blinded by all of this, and you can't really use it anymore. Well, you could go up and you could replace that coolant every now and then if you wanted to, but when you're L2 point a million miles away, that's not an option. So instead of doing that, they went with passive cooling. They put this thing in the shade perpetually, always in the shade. Sunlight never hits it. That's one reason why they wanted to get it far away from the Earth, because the Earth is big in low Earth orbit, and you're going to get infrared radiation from the Earth. But from a million miles away, the Earth is only going to be, about a ½ degree across. And it's going to be perpetually behind this because, remember, we're on the other side. The sun's here, the Earth is here, it's over here. The shade's going to always be there, blocking both the Earth and the sun. So you let it sit there for a few months, and it radiates away heat, doesn't absorb much in the heat, and it's only a few degrees above absolute zero. It's very cold there. Isn't that clever how they did that? So this allows that once it cooled down, it took months to cool down, but once it did that, able to take good infrared images. So at the telescope, it's not cooled, it will emit infrared. I already said that. And the earlier space probes were cooled with a refrigerant, I already said that too. And that shortens the lifetime of the thing, but it doesn't in this case because it's passive. The entire thing's passive, and that's really clever. And there, again, there's no repair mission or coolant refill missions that we could ever do. Okay, why the infrared? Why not the visible again? Well, I'm going to explain to you very carefully here. And the first thing you got to do is play make-believe with me. Assume the Big Bang universe, that 13.8 billion years ago, the universe popped into existence in a very hot, dense state, expanding, and as time went by, it cooled, and eventually formations of galaxies and stars and planets and people. That's the general consensus among astronomers out there, the history of the universe. I suspect everybody in the room is going to disagree with that because we're creationists, we're recent creationists, and this doesn't jibe with the Bible at all. But they built this to test some ideas related to Big Bang cosmology, but even more than that, galaxy formation. See, the whole idea is that the Big Bang happens, and as it cools, it spreads out the gas, but eventually the gas begins to collapse into structures that give rise to galaxies and stars and so forth, and it's that part that they want to investigate. So technically it's not testing Big Bang ideas, it's testing what comes after the Big Bang, theories of formation of galaxies and stars. And this is part of a naturalism, part of an evolutionary worldview applied to cosmology and astronomy. A second thing you have to assume is that distance translates into look-back time. When you look at the moon tonight, if you can see it between the clouds, you're not looking at the moon as it appears right now, but you're looking at the moon as it appeared about a second and a third ago. Not very long. If you glimpse the sun, hopefully with a sun filter, you're looking at the sun not as it now exists, but as it existed little over 8 minutes ago. If you look at Jupiter, you're looking at Jupiter as it existed 40 minutes ago. If Jupiter suddenly just blew up or disappeared or something, it would be 40 minutes before we would know about that. The nearest star, a little over 4 light years away, you're looking at the star as it appeared 4 years ago, not as it appears now. And in the autumn skies, a dark location, I can pick out the Andromeda galaxy. It's a little over 2 million light years away. And we're not looking at it according to what it looks like now, but it looks like it was when it's 2 million years ago. And you keep extending that out. So if you go out to, say, 10 billion light years, presumably by the secular idea, these 2 points made right there, you're not looking at those galaxies as they now exist, you're looking at them as they existed 10 billion years ago, just less than 4 billion years after the Big Bang. If you go to 11 billion light years, even earlier, 12 billion light years, and so forth. So the whole point is they want to look at the galaxies really, really, really far away. They want to look at the galaxies as they existed within 1 billion years of the Big Bang. So you got to look back now at least 12.7 billion light years. Now, if you look back that far in time, you're looking at a great distance, and you've probably heard of the Hubble relation. The Hubble relation was discovered by Edwin Hubble almost a century ago, and what he found was a correlation between redshift and distance. It's usually attributed to the expansion of the universe, but I'm open to some other interpretations as well. And so as you look farther and farther out, the galaxies their light is shifted from the visible part of the spectrum more towards the red end, and then into the infrared, and farther into the infrared and infrared. And when you go looking at galaxies that are 10 or 11 billion light years away from us, their light has been shifted by a factor of 10 or 20. Which means all this light, the main part of the light of a galaxy is in the visible part of the spectrum, but if you looked at them in the visible part of the spectrum, you likely wouldn't see much at all. Because all that light that was originally was emitted in the visible part of the spectrum has been shoved over into pretty far into the infrared. So they designed this telescope with a couple of objectives, but the main objective was to look at the very earliest galaxies given the light that they emitted, not the light that we're now receiving. You got to shift your vision over in the infrared. That's why they went to the infrared, because those early universe galaxies were greatly redshifted. So in order to observe those, you have to look deep into the infrared. Does that make clear to everybody why they're doing infrared here? Because the expansion of the universe, and because they think they're looking at a look-back time. Now, there's another concept. I talked about the Big Bang. Originally, according to the Big Bang model, the universe begins in a very hot, dense state. The radiation in that universe, that gas that's there, is very bright. But as it expands, it cools, and then the universe grows dark. The universe starts off very brightly in the Big Bang model, but within a few million years, it starts getting dimmer and dimmer, and you have what's called a cosmic dark age. And it's believed that cosmic dark age lasted for about 500 million years. 500 million years, the universe gets very dim, and then stars begin to form, and as stars form, they get bright again, so you get this revival of light. So the universe starts off very bright, it dims, and then stars begin to form, and the universe gets brighter again. So you get this cosmic dark age that lasted for a few 100 million years. Keep in mind, I'm just giving you the evolutionary timeline and the evolutionary ideas. I'm not teaching this as truth. I'm simply saying that's what most astronomers believe the history of the universe is, and that's why they built the JWST to test those ideas. So how well do the observations agree with the theoretical of what was going on in that cosmic dark age? That's the big question we have here. So the questions the JWST must answer is, how did those early galaxies form? What did they look like when they first formed? They've got this idea of how galaxies form, and as the galaxies begin to develop, their appearance would change with time, is the whole idea. So what did those early galaxies look like as they formed? And what structure did they have? Today we see structure, particularly in spiral galaxies. They want to know, what did those early galaxies, what kind of structure did they have? Were they fundamentally different from the galaxies we see today? And the theory says they should be. Galaxies should evolve over time. And then what was the composition of those galaxies early on? Because you see, in the Big Bang model, the universe begins with just hydrogen and helium and nothing else. And I'll come back to that in a few minutes. But you must have these heavier elements that develop throughout time according to the naturalistic theories we have. And then how have galaxies evolved since then? So you got these questions they want to look at. They're testing not so much the Big Bang, but the stuff that comes after the Big Bang. How do stars and galaxies form, and how do they develop early in the universe? Now, you've probably seen some pretty photos that came out when they first started using the JWST. They had to make some test images. They went to some well-known things, some nebulae that they photographed and so forth, and showed those. They were very pretty. Again, they were false color, but that doesn't matter. They also looked at this particular object. It's a cluster of galaxies, and you see those blue spike things? Those are stars within our own galaxy. And then the thing in the middle, there is a single large galaxy in the middle, that fuzzy thing. And then that's in the middle of the picture. And then on the outskirts around that, you see a bunch of smaller galaxies. And you'll see these little arcs like this, are kind of like a bullseye pattern. What you're seeing there is gravitational lensing. That very massive galaxy happens to lie in the same direction as the more distant cluster of thousands of galaxies. And some of the light passes close to it, and it gets bent by the gravitational pull of that massive galaxy, and you get these little arcs. That was predicted by Albert Einstein more than 100 years ago. It was first actually photographed in the 1980s. It took that long to finally be able to do it. Now it's almost routine. By the way, this particular cluster was photographed by the HST, and the image from the JWST is much better. So that tells you how much better the telescope is. All right, enough for the pretty pictures though. Let's get on to the meat of the matter. Here are two images. One is Macy's galaxy on the top. The one below is Sears 93316. Just rolls off the tongue, doesn't it, that name? And you've got several band passes. The wavelengths are running across the bottom. Notice the bottom there is on the left is 1 micron, and that's in the near infrared. By the way, the visible extends to about 0.6 or 0.7 microns, so the visible would be off to the left of the scale quite a bit. And then you have 1.5 microns, 2, 2.5, 3, 3.5, 4, 4.5. It's on a log scale. And you've got 6 different images there for both those galaxies running across the top. The first one's over in the very near infrared, a little around 1.2 microns. The next one around 1.5. The next one around 2. The third one over is around 2.7 or so. And then the next one, the fourth one, the fifth one, is around 3.5 microns, and the last one on the right is around 4.5 microns. And you can see some differences in structure. You can see some things that are circled for identification here. Most of us would not really think much of this. And also superimposed on that is the spectrum there. You'll notice across the bottom of this first one here, that's the one, they've got the H Lyman alpha line identified. They've got oxygen here, and then the galaxy down here, they've got hydrogen and oxygen and sulfur lines indicated there. Looking at the spectrum, because we can use that to figure out what these things are made out of. Now, what's remarkable about this is the cosmic age. The cosmic age is determined by estimating the redshift of these galaxies, which by the Hubble relation correlates to a distance. Then it's a look-back time, and you subtract that off the Hubble, the age they think of the Big Bang, and notice that the cosmic age of that Macy's galaxy up there is 392 million years after the Big Bang. Now, what did I say about the dark ages, the cosmic dark age? Something like 500 million years. So what's Macy's galaxy doing there? And then the Sears 93316, originally they thought it was about that vintage as well. They realized they made a mistake on that, so they bumped it up to 1.19 billion years now. But it's still pretty early according to the evolutionary time frame. But it's interesting what they're finding out about the cosmic dark ages. Again, it was the time between the Big Bang and the first galaxy formation. Should last for about 500 million years. But the problem is the JWST has observed galaxies that they think are 200 to 300 million light years, 200 to 300 million years after the Big Bang, which means there was no cosmic dark age. At least it didn't last as long as they originally thought. Again, they didn't expect to see any galaxies as back as 500 million years after the Big Bang. They're seeing them at 200 and 300 million years. The whole point is galaxies form too fast. Now, how are they going to solve this problem? They're probably going to argue that, well, we'll just change the theory to make it match the data. But right now, the data are clearly are contradicting the evolutionary theory of how when galaxies formed. I suspect they're going to start finding stuff around 150 and 100 million light years, million years after the Big Bang as well. Then there's a structure of distant galaxies. Not only are they forming too fast, but what kind of structure they have. Remember, they're supposed to form, and then that form changes or evolves over time. But what they're finding is that those distant galaxies appear to have full structure like galaxies nearby have. There's little evidence of galaxy structure evolution taking place. It seems like the most distant and hence the earliest galaxies in the universe are fully formed. They're not forming, they're fully formed. Now, my colleague Jason Lyle, many of you know that name, before the JWST went up, he actually went out on a limb, he made a prediction. He said, we're going to find fully formed galaxies all the way back. He based that upon the very good of creation created, or the very good created, pronounced on end of day 6, but the good of creation God proclaimed on the end of day 4. And that goodness refers to fully functioning, that things that God made are operating and doing the things that God intended them to make. And that's exactly what we find. I wish I would have gone out. I didn't think about it. I mean, I knew that, but I didn't think of actually going public with a pronouncement. I'm glad one of us did. Jason had the forethought to do it. And he was out, when I read that, I thought, yeah, you're right, Jason. I wish I would have said that. But he said it first. Give him the credit because he was right. We all agreed with him, but he was the one that actually publicly said it. And that's a stark contrast to what the evolutionary astronomers are saying. But as nice as these two things are, the galaxies forming too soon and being fully functioning, I think there's something even more significant, and that has to do with the composition of distant galaxies. Remember, they can do not only images, but they can do spectroscopy as well and identify the elements that are present in the spectra there. Now, you got to realize the Big Bang model results in nothing but hydrogen and helium with just a little bit of lithium. According to the Big Bang model, the universe began with no beryllium, no boron, no carbon, no nitrogen, no oxygen, nothing, all of those things. All the heavier elements are missing. And the theory of where they came from was that stars formed, and they get their energy from the transformation, the nuclear fusion of smaller elements into larger elements. In fact, the sun gets its energy by fusing hydrogen into helium, and we have direct evidence that, in fact, that's what the sun is doing, and presumably other stars are doing. Now, more massive stars, according to the theory, can start synthesizing carbon, and from that they can make nitrogen and oxygen and calcium and iron and silicon. Don't worry about silicon, but what about carbon, nitrogen, oxygen, calcium, and iron? Where do you find those things? In our bodies. You've got carbohydrates that have carbon and oxygen in them. Also, nitrogen plays a key role in there too. You've got calcium in your bones and you've got iron in your blood. I just selected some of the more common elements that are found in our body. In fact, all living things have these elements in them, and a few others as well. The whole point is, the evolutionist will tell you that we are made of stardust. You all heard some people say that we're made of stardust, and their point is that the Big Bang happens, the life could not exist because the heavier elements weren't there. A few stars formed, very massive ones. They fuse some of the heavier elements, they blow up, they spread the products of their nucleosynthesis into the interstellar medium, which is a fancy smancy name for the gas between the stars. And it mixes there with that, and another generation of stars form, and they go through the same process, and they belch out their products that then mix with the gas in the interstellar medium, and the process goes on and on. You see, very gradually, over billions and billions of years, you build up more and more of the heavier elements. It's called chemical enrichment. That's why they say we're made out of stardust, because they have to naturalistically explain where the elements were made out of. In fact, life in the early universe was not possible because the elements necessary for life were not there. You've all heard of Lawrence Krauss. He's been a little crass about the way he says this, and forgive me for quoting him, but in a presentation more than once, I believe, I've seen it on video and he's written it, he said, "Forget Jesus, the stars died for you." Because those stars blew up and they seeded the universe. That's the theory, ultimate evolutionary theory. It didn't start with Darwin. It didn't start with some pond on the earth, warm pond with nutrients in it. It started way back billions of years ago, long before the solar system and the earth even existed. You had to build up these elements and all of this. Well, how well is that coming along here? Well, they use the spectroscopy here. Remember those galaxies that are 200 and 300 million years after the Big Bang? Guess what we find? They're rich in heavier elements. So just like Jason said, it's galaxies all the way back. We're finding elements all the way back as well. Again, showing that there's a problem with the secular worldview here. They also find evidence of dust, and dust is very interesting because you can't make dust out of hydrogen and helium. You need things like silicon and iron to make dust, and a few other things can be thrown in there. So you got to build up a lot of that, but even more importantly that, even if the very first generation of stars made iron and silicon and oxygen, you're not going to get dust right away. It takes at least another generation of stars to form it, because I think dust is formed in the atmospheres of cool giant stars. So you need multiple generations to produce this, yet we're seeing in the earliest galaxies evidence of dust and the heavier elements. They're even finding organic molecules at great distance in the universe, great look-back time. And that takes time to produce according to the secular model. So what is it doing there? I think most significant thing to me, the morphology is fine, and the galaxies will not belong, forming too soon is fine. But to me, even more significant than that is a much more subtle chemical evolution. There's just little evidence that there's any chemical evolution occurring. It's as if the universe was created fully formed. I know this crowd is not surprised to hear that. But the secular world, it's knocked them back on their heels. They have to rewrite the textbooks, everything on this. Now, I do want to address something that happened just a couple of weeks ago. It made the news, and you may have heard about this, a study of 263 galaxies that showed that most galaxies rotate opposite the direction of the Milky Way. Now, they weren't dealing with people have heard about that one, okay? Some of you have. This just came out a couple of weeks ago. And the galaxies here were not at the most distant part of the universe. They're much closer to us. The JWST can actually look at much closer galaxies if you want to, because you've got the near infrared and even into the visible part of the spectrum. And in this diagram, they showed you some of these have been circled, the red ones and the blue ones. And from the images, they can actually ascertain which way they're spinning. Galaxies rotate. And there's a belief about the universe that's called the cosmological principle. It says two parts. It says the universe is both homogeneous and isotropic. Homogeneity refers to the fact that matter is evenly distributed in the universe as long as you kind of ignore the local stuff. Well, there's a problem with that. We see clumping all the way up. It's been believed all my lifetime, and much before I was born, that at some great level, some level of the universe, it will kind of smooth out. But we haven't found that level yet. It's still clumpy all the way. So there's a question whether the universe is really homogeneous. The other one, isotropy, means that there's no preferred direction in space, which means that half as many galaxies ought to go one way as go the other way. But what they found is something like 3 to 1, they go in a direction that's opposite the way the Milky Way is spinning. 263, that's a large sample size. If you had 10 or 15 galaxies, you might say, well, just sample size is too small. But 263, that's a huge sample size, and they haven't a clue what this means. Now, what about the significance of this? Well, the cosmological principle, that is homogeneity and isotropy in the universe, is a foundational assumption of the Big Bang. If the universe is neither homogeneous nor isotropic, then what does that suggest about the Big Bang? Can you have a true theory that's based upon a false premise? And by happenstance, maybe, but it doesn't follow directly and defies logic. So it's kind of calling in question one of those foundational things of cosmology today. Now, I said earlier that there are two primary objectives that the JWST was built to do, and one of them is to probe the inner workings of the galaxies and star formation in the early universe. And we've seen tonight that there are real problems everywhere. It's totally set the secular theories on their heads. The other one is to probe the atmospheres of exoplanets. What are exoplanets? These are planets orbiting other stars. For much of history, that was just conjecture. We thought, okay, the sun is a star, it's got 8 planets orbiting around it. Might there be other stars with planets orbiting them? And people thought that might be the case. But the first actual discovery of an exoplanet was just 30 years ago. Does anyone have any idea how many exoplanets there now are known to exist? More than 5,000. We're going to hit, I blogged a couple of years ago when we hit that 5,000 mark. We're going to hit the 6,000 mark here soon. So there are thousands and thousands, more than 5,000 of them. By the way, if you would have gone back, say, 30, 35 years ago, before we started discovering exoplanets, and you would ask a bunch of astronomers or other scientists, when we found over 5,000 exoplanets that were out there, how many would be Earth-like? What kind of answers do you think you would have gotten? Oh, bunches, hundreds of them. How many of those 5,000 plus are Earth-like? 0. None of them are. There are a few that they claim, but it just takes me a few minutes of searching on the internet to give you reasons why they aren't. They don't tell you the whole story in those news releases, but each one of them, there's just something wrong with the star or with the planet or both. There's a problem. Well, how do they discover exoplanets? There are different mechanisms, but the most common one is looking for what are called occultations. Now, I've got here a little figure showing what an occultation will look like. You got that yellow ball, which is a star, and suppose a planet, by that little red ball, is going around like this. And notice that the planet is a lot smaller than the star. That's pretty common because the Earth is, well, the Sun is more than 100 times larger than the Earth is. The Earth is tiny compared to the Sun. Even Jupiter's only about 10% the diameter of the Sun. Now, if you happen to observe an orbiting planet, a system like this, and you happen to lie near its orbital plane, then once each orbit, that planet will pass in front of the star. Now, if the planet's orbiting like this, you're not going to see anything, right? But if it orbits like this, so it passes in front of the star, then once each orbit will pass in front, kind of like an eclipse. We call it actually an occultation because it's smaller appearing than the star is. And it's going to block out part of the light of the star. And on the bottom there, you can see a little light curve right there. Notice you go from left to right on the time. It's constant, then it dips down, and then it recovers. That's the occultation taking place. Now, this is very similar to the kind of work I do. For 45 years, I've been studying eclipsing binary stars. And we see eclipses on those when we're in the orbital plane, and we can learn a lot of things about them, like the sizes of the stars involved and everything. So when I saw these, I thought, well, I know this stuff. I do something very similar to it. That's what it looks like kind of theoretically, but here's actual data on one of the early occultation discoveries. And what you have to do is be able to measure the brightness of a star very accurately. From orbit, you can really do that. From the ground, you can, but it's very difficult. From orbit's a lot better. We've had a couple of orbiting spacecraft. Kepler was one. We have another one up there now. The name escapes me. It's doing the same sort of thing, measuring millions of stars frequently, and measuring to like 1 part in 100,000 the dip in brightness. By the way, the Earth would be, if you orbited it from an alien planet in another solar system, looking at the Sun, if you happen to land its orbital plane, it would only drop by 1 part in 10,000. You could easily detect the Earth by this way. That's how we do most of these. Well, as that planet moves in front of that star, its atmosphere around the edge, perimeter of that planet, is actually going to absorb light at certain wavelengths. Now, our atmosphere is usually molecular, like we have diatomic nitrogen and diatomic oxygen. That means that each molecule of nitrogen and each molecule of oxygen, or atmosphere, has 2 atoms bonded together. As it turns out, molecular spectroscopy generally is in the infrared. Just what the James Webb Space Telescope is. It's in the infrared, so why not use it with all this aperture and all this precision to be able to do this? So the hope, I think they've started on a little bit, had a few results, but what they're doing is they're looking at some of these known exoplanets. They know when they're going to pass in front, so they take a spectrum when there's no occultation taking place. They take a spectrum when there is an occultation taking place, and when you subtract the two, you'll be left with the absorption spectrum of the planet's atmosphere. And they've actually done this already. That they found a few with methane and things like this, like the Jovian planets have, Jupiter, for instance. But the gold standard is looking for that diatomic nitrogen and diatomic oxygen, because that, folks, is a signature of a possible, not definite, but a possible Earth-like planet. My expectation is that they're not going to find any of those. The fact that we've not heard anything about it is kind of like a silent argument that they haven't found it. They're going to keep looking, because that's one of the big things. That's the thing I'm watching for, the big blockbuster. Are they going to find many atmospheres around some of these stars that they can detect around these planets? And if they do, are they going to find any diatomic nitrogen and oxygen? Again, I expect they won't. And I have the opinion that the Earth is unique in the universe. I don't care how many quadrillions of planets you hypothesize, it's still unique. And I do believe we are unique in the universe. I don't think life exists on any other planet. And I'm confident that the evidence from the James Webb Space Telescope will do the same thing. Well, thank you very much. I'll be happy to answer questions about this or other subjects as well.